All right, 10.1 is called lines and segments that intersect circles. Our goals today are to be able to identify these special types of segments and lines that intersect circles. We're going to be able to draw and identify something called common tangents, and then we're going to use properties of tangents. Okay? Some of this will be, hopefully, review. A circle. By definition, a circle is the set. Guys, in math, set just means kind of the list or the amount, the number of, okay? The set of all points in a plane that are equidistant from a given point. This given point is the center. Now, there's a couple ways to name circles. The first way is just by saying, hey, circle P, and we're going to use the center, okay? We're going to use the center of the circle as that point, so this would be circle P, okay? In the textbook or maybe online, you might see that symbol right there. On a test or a quiz, I don't know how to make that symbol on my computer, so I just say circle P. But if you see that little symbol right there, that means circle. Okay, now moving on to a chord. A chord is a segment whose endpoints lie on the circle. Okay, a chord is a segment whose endpoints lie on the circle. So for example, this would be a chord. It is a segment whose endpoints lie on the circle. Is that a chord? Do both endpoints lie on the circle? No. Is that a chord?
Yes. Wait, is that a third point in the middle?
Well, it goes through the middle, so yes, that's a point. Is this a chord?
Yes.
Sometimes this is called a what? I heard someone say it. It starts with a D. Diameter. This is a diameter. But is it a chord?
Yeah. Yeah. Because it's endpoints around the
Am I a person?
circle.
Yeah.
I'm a person. I'm just a special type of person called a teacher. Okay? So I'm a person. This is a chord. Because both endpoints lie in the circle. Now, it is a special type of chord called a diameter. Okay? So yes, a diameter is a chord because both endpoints lie on the circle. A diameter is a chord that goes through the center. It's a special type of chord that travels through the center of the circle. So that would be a diameter. Okay, a radius is a segment whose endpoints are the center and any point on the circle. Okay, so it's a segment whose endpoints are the center and any point on the circle. So that would be an example of a radius. All those, I believe, should be familiar. We've seen them at one point or the other. Now these, not so much. Okay, the first one, or the next one's called a secant line. A secant is a line that intersects a circle in 2 points. Okay, so it's a line, could possibly be a ray, where it intersects at 2 points. So it's going to go straight through the circle like that. That's called a secant line. What's the difference between a secant line and a chord?
The chord's endpoints are on the circle, and the secant goes right through.
Great. A chord ends. A secant line doesn't. And I can't say it doesn't end because, you know, let's say this is a segment. Is that segment a chord? No. Because the endpoints are on the circle, it would be a secant segment. We don't see a ton of those. But you guys get the idea. The next one is called a tangent. Now, we talked about sine, cosine, tangent. There is a connection and where this comes from. I'm not going to get into that. But a tangent is a line that intersects a circle in one point. Erase that S. In one point. How in the world can a line intersect a circle at one point?
You only go through like one of the surrounding.
So like this?
You don't go out. Yeah.
But what's wrong with that?
Oh, make the other one like a point. Yeah.
Okay, but it says it's a line.
Ooh.
So a line that intersects a circle in one point. Any ideas?
If it's on the circle line.
On the circle line. Can you explain that a little more, Hans?
On the line. And that's all I can really say about it.
Okay.
Just on the line.
I think you're right. I think maybe a better way to say it is that the line just touches the circle. Okay? So if I think about a line that comes and it just brushes up against or just touches that circle, if it touches, it's going to touch at exactly one point. Okay? Think of, let's see here. Think of a ruler resting on a basketball. If you zoom in on that basketball, that ruler is actually just going to be touching that basketball at one point. Okay? And that is kind of a tangent line. Now, this point where the line touches the circle, that is called the point of tangency. Okay, guys, we will use these terms in these lines throughout the chapter. So it's not like we just need to know them today. We need to know them throughout the chapter. Okay? All right, top of the second page. It says, tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. All right, so if I look at this first one, I'm looking at ray AC. Excuse me, I'm sorry, I lied. Segment AC. Keaton, what do you think?
Radius.
It's a radius. It goes from the center of the circle to the edge of the circle. I believe that would be a radius. Okay, let's go across here. Segment AB. Kaylin, what do you think? Segment AB goes from one part of the circle to the other, so it's a chord, but it goes through the center, which makes it a diameter. Great. All right, ray, DE. Cole, what do you think? Ray, DE.
That was a line of tangency.
Line of, we just call it a tangent line. Okay, I like that. It's just a tangent line. Tangent line. Okay, next one. It says line AE. Line AE. Ellie, what do you think? Say it again. A chord, AE, we're talking about a line. It goes through, and since it's a line, though, it's going to go on forever. Would you agree? And a chord has endpoints on the circle. I think secant is a better name for it. All right. What about segment AG? Eli, what do you think?
Chord.
A chord. Or is it a secant?
Well, it says segment, so wouldn't that mean like
Oh.
A?
Great. If you guys look at these last two, I've got AG and AG. But one of them says segment. So on this one, I'm not concerned about any of that, and I'm not concerned about any of that, because I am just worried about that. So that would be a chord. But if I look at this next one, it says line AG. So now I'm concerned about everything. So this whole thing that goes on in both directions infinitely, well, that would be a secant. Are there questions about anything in this example? Awesome. Okay. Now, this next box is called coplanar circles. What's coplanar mean again? Target the person next to you. What does coplanar mean? Means what?
When something's on the same plane.
Okay, we're all done? Maggie, what'd you say?
I said on the same.
It's on the same plane. So two circles that are on the same plane. Here's what I want you to first think about. What would it look like if two circles were not on the same plane?
Two.
Maybe turn to the person next to you, talk about it. Maybe you can give a real world example using real life examples. But what would it look like for two circles not on the same plane? Go. Not necessarily. Volunteers. I've got one, now I have two. Three people that are willing to help us out today. Now I have 0.
Do I stand up or what?
Well, you don't need to. If you want to stand up, you certainly can. Hi. Give us an example of two non-coplanar circles.
Like,
Do you want us to draw it on the board?
Well, I thought you had an example that you could verbalize, so that's why I was kind of...
oh, I thought
Okay.
you wanted me to show one. Like, in the classroom.
Hey, sure. Any...
Uh,
Hannah said the circle that's drawn on the board and the circle that's on the top of my stool. Are they both circles?
Yeah.
Are they on the same plane?
No.
No, they're not. I think that'd be a great example. Someone in the other class gave that clock and that clock. They're not on the same plane. They're not on the same flat surface. Okay, now, those two examples we just gave were two examples of circles that didn't intersect and weren't on the same plane. I want you to think about two circles that aren't on the same plane that intersect. What would they look like? Go. Any ideas? Any examples of two circles that aren't on the same plane that intersect?
So like this circle right here. Let's just move this chair over here and pretend that was a little bit up higher. And we had that circle and this circle, so they're like, you know.
Oh, I
What
like
I'm
that.
talking about?
Imagine that circle on the wall and the bar stool or the stool there. We're touching. They're not on the same plane. They're not on the same flat surface, are they? No. I think that's an example. Any other examples?
so, when they both of them, like, when two lines intersect, then they would have to be, like, close to each other. Like, they would have to be, like, kind of, like, over each other, like, the planes would have to, like, intersect each other.
Okay, the planes that they're on would have to intersect. I like that idea. Some of the other class said handcuffs.
Oh, yeah, that's a good one.
It is a good one because in a handcuff you've got these two circles, right? But I think that's a great idea. They're on different planes, unless they're on the same plane. But can they intersect? Well, if you open one up and put one inside the other, won't they look something like this? Everyone do this with your hands with me. Would you agree that these two circles, they intersect, but they're not on the same plane? Would you agree? They're on different planes. One's going up and down, and one's going side to side here. Okay? I kind of went on a tangent there. Get it? But I think that's important to understand. What does coplanar mean? Not every circle, not every two circles are going to be coplanar on the same plane. But everything in this class will be. So, coplanar, two circles that intersect in 1 point, 2 points, or 0 points. I got an example of 2 points. If they're coplanar, they intersect in 2 points, that's what it's going to look like. If they're going to intersect in 1 point, well, it could look like that. Or it could look like that. Now, they got a tangent line there because if they intersect at 1 point, essentially that point is the point of tangency. So there's going to be a tangent line there. And lastly, if they intersect in no points, well, it's going to look like this. Or what they're called is called concentric circles. Concentric circles have the exact same center. Okay, those don't intersect. Okay, this next idea is called a common tangent. Common tangent is a line or segment, I guess it could be a ray too, that is tangent to two coplanar circles. So one line or segment, or ray really, that is tangent to two circles. So example 2. Tell how many common tangents the circles have and draw them. So if I'm looking at example 1 here, or example 2, but this part of example 2, we're going to draw them first, and then we're going to tell how many. Okay? Can anybody take my computer and draw me a tangent line? Eli's first. Draw me a tangent line. We're not going to laugh at how crooked you draw this line, I promise. Okay? Turn the pen over. Turn the pen over and erase it. Well, I don't want you to make it a fat line. A nice skinny line.
Oh, I don't know if I can do that. Oh, wait, no, I can't. No, I can't. Just forget about that point.
Okay? Not drawn the best, but would you guys agree that there would be a tangent that looks something like that? Okay? Anyone else? Is there another tangent line here? Oh, yeah. Oh, he's going to draw us a tangent line. Oh, wow. Can you extend that a little more at the top? Hold on. Perfect. Oh, she's putting you to shame there. Or Eli, she's putting you to shame. Tangent line. Would you guys agree there? Is there another one? Yep. Who's going to draw it for me? Maggie's going to draw it.
Okay, break. Okay. Pretend there's not that little thing.
Perfect. Thank you, Maggie. Do we have another one?
Yes.
Ryan's going to draw it.
Oh, okay.
Not with your pencil, Brian. I'm just kidding.
Oh, this is going to be bad.
Perfect. Another shaky tangent line, but that would be a tangent line. Are there any others?
No.
Now, in the other class, I had someone say, well, Mr. Cole, isn't like that a tangent line? Because it only touches every circle once. And I said, well, no, it's not. Tangent line just has to brush up against the outer edge of a circle. So I think in this example, oops, I just erased Brian's. I think there's 4 of them. 4 tangent lines. What about on this next one? Well, I think there's some obvious ones here, or this one. And that one. Are there any others though?
In the middle.
In the what? In between them. So these guys, these are touching at a point, these two circles. Well, there is also a tangent line that goes right there, kind of like up above when we're talking about intersecting circles at one point. There's an example of that. So I think here there would be 3 tangent lines. And then on the next one, well, I think there's that one again. That one. Any others? What about this one? No, it touches each circle twice. I think here there's only 2 of them. Okay, top of the 3rd page. Talked about tangent lines, talk about what they look like. We drew some. Now we're going to talk about some properties of tangent lines. Okay, so a line is, I'm going to stop us here. If I have a circle, and this kind of goes back to proof, if I have a circle, you don't need to draw this, just watch because I'm going to erase it, and I have a circle that looks like this. Is that tangent? Well, we talked earlier about, yeah, we won't, what if it looks tangent, it's going to be tangent. Okay, well now we're going to have proof. Here's a little bit of proof. And it says this. A line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. Wolf, what does that mean? Well, this line that I drew is tangent if and only if it is perpendicular to the radius, if that point right there is the point of tangency. So if I look at this example, well, is this line, line M, a tangent line? I think it is. Actually, I know it is because it is perpendicular to the radius at that point. Okay, so there's some proof. Second property that deals with tangents is that a tangent segments to a circle. So if I look here, AB and BC are tangent segments. Now, how do I know that AB and BC are tangent? Well, maybe it's best to draw that right there. Because if they're perpendicular to the radius, then I know they're tangent. Okay? But if tangent segments to a circle from a common external point, okay, so I've got these two segments, they both come from an external point P, then these tangent segments are congruent. So AB is congruent to BC. So it's a tangent line if it's perpendicular to the radius. And if we have two tangent lines or tangent segments from an external point, they're congruent. Example 3. Is segment ST tangent to circle P? Is ST tangent?
No, because tangent is a line, not one that is.
Okay? It could be a tangent segment.
Oh, okay.
What do we know to be true about a tangent line? Look up above. It's going to be perpendicular. Don't I have a triangle here? How do I determine in a triangle if that is a right angle? Maybe. In the Pythagorean theorem, probably a little more simpler. Pythagorean theorem. Could we use sine, cosine, tangent? Well, we'd have to find the angle, possibly, yes. We could. But let's just do Pythagorean theorem quick. Which one's our hypotenuse? 37. So 37 is going over there. And I'm going to put 12 squared plus 35 squared. Because if the Pythagorean theorem works, then it's a right triangle, which makes it tangent. So we get 144 plus, I don't know 35 squared, I'm not that smart. 1225. And 37 squared,
1,369.
1369. So when I add these two together, what do you get? 1369. So the Pythagorean theorem works. What does that mean? Yeah, that means that's a right triangle, which makes that a right angle, which makes this tangent. Is it tangent? Yes, it is, because of the Pythagorean theorem. We've proven that that's a right angle. Questions there? Okay, guys, this is the best problem of the day. So it says in the diagram, point B is the point of tangency. So I know AB is tangent. So if AB is tangent, I know what will work. The Pythagorean theorem. Does that make sense? If it's a point of tangency, I know there's a tangent line, so I know the Pythagorean theorem is going to work. It says find the radius r. First of all, which side is our hypotenuse? Because I don't know which one's the longest side here.
AB is 80 feet.
Well, where's the right angle? Because it says there's a tangent line. That's at B, right? So I know, that's a bad one, I know that's a right angle. So then I know AC is my hypotenuse.
Oh, I thought it was saying like AC combined is 50 feet, so I was confused.
No, and this is important.
Yeah.
50 goes from here to here.
Yep.
R, well, that's the radius. That goes from there to there. R goes from there to there. And then 80 is the whole thing. So if I were to do the Pythagorean theorem, which is a squared plus b squared equals c squared, a and b, well, my hypotenuse is this. That's my hypotenuse. So I need to put r squared plus 80 squared equals my hypotenuse. What's my hypotenuse?
50 plus r squared.
Well, would you guys agree that my hypotenuse is going to be 50 plus r? Or r plus 50? And what do we need to do to our hypotenuse? We need to square it, don't we? So I'm going to put r plus 50 squared. Because our hypotenuse is the whole darn thing. Oh boy, how are we going to find r? Well, on the left side, I'll have r squared plus 80 squared is, guys, 8 times 8, don't use a calculator. 8 times 8 is 64. So 80 times 80 is 6,400. What in the world do I do here?
Square root r squared and square root.
No. Because if I have x squared, isn't that the same thing as x times x?
Yeah.
Because exponents mean repeated multiplication. So if I have r plus 50 squared, that's the same thing as r plus 50 times r plus 50. Well, what do I do on the right side?
We have foil.
We have to what?
Foil.
Foil, one of my favorite 3 F words. You guys know I have 3 favorite F words?
Yeah.
Factor, foil, and function.
Function.
3 favorite F words. We have to foil. Raise your hand if you remember how to foil.
First, outside.
Okay, more than in the other class. We don't do it a lot in geometry. We do it in Algebra 1. We do it a bunch in Algebra 2 and pre-calc. We need a FOIL. FOIL stands for first, outside, inside, last. This is on our assignment. This is going to be on the test. We need to know how to FOIL, which is kind of weird because we haven't done it all year. So you FOIL when you're multiplying two things like that look like that together, a binomial. So the first two things. So the first two in each binomial, r times r. R times r is
R squared.
r squared. R plus r is 2r. R times r is r squared. Okay? Now we do our outside. So that means r times 50. What's r times 50? 50r. What's 50 times r? Okay, let me back up. I'm getting ahead of myself. Inside mean the inside two. 50 times r is 50r. And then L stands for last, the outer two. Or I should say the last two, not the outer two. The last two, 50 times 50, which is 2,500. So on the left, things stay the same. R squared plus 6,400. Now, on the right, in the green, can I combine like terms at all?
Yes.
Yeah, 50R and 50R. Well, if I had 50 Mountain Dews and another 50 Mountain Dews, that's 100 Mountain Dews.
Yeah.
Actually, that's diabetes. No, I'm just kidding. R squared plus 100R plus 2,500. I'm going to stop here. Are there any questions with what I've done so far? It's a little different. We haven't done this a bunch. I need to solve for r. Okay? So if I take a look at r squared here, I have an r squared here and an r squared here. So if I minus an r squared there and minus an r squared there, if I minus this to get it over there, what happens? They both cancel. They go away. I'm just going to let you know, on every type of problem that we're going to do in this section, that's going to happen. So now if I take a look here, I have 6,400 equals 100R plus 2,500. Yeah. Now we're just solving an equation. I got R's, I got numbers. Let's get all our numbers on one side, all our R's on the other. So I'm going to subtract 2,500. What do we get there? 3,900. Yeah, 3,900 equals 100R. Divide both sides by 100. R equals 39. And I think that's our goal, right? It says define the radius of circle C. Questions on this one? I got two more. I've got two more in there short, and they're quick, okay? So here, remember if I look up above at the top of this page, it says that if I have two tangent lines or tangent segments from an external point, what do I know about those segments? They're equal, right? So they're the same length. So that means 3x plus 4 equals 28 because they are congruent. And we're supposed to find the value of x, so I'm going to solve for x. 3x equals 24. Divide both sides by 3, and x equals 8. Questions there? Because they're both tangent, they're equal. And lastly, on the top of the last page, the circle is what? Inscribed. Inscribed. Well, what's scribe? What's a scribe?
Person who writes.
Person who writes stuff, okay? So inscribed means that the circle is drawn inside the triangle, okay? And more specifically, it means that every point where the triangle touches the circle or the circle touches the triangle, it's just a touch. So that means I have essentially 3 tangent lines. Or 6 segments, yeah. So what I'm looking at here, if I look at A, if this is 10, what does this have to be? 10. If this is 8, what's this have to be? 8. If this is 15, this has to be 15. And again, our goal is to find the perimeter of the triangle. Well, I think now I've found the distance all the way around the thing. So this side, I think, is 25. This is going to be 23. And this is going to be 18. So now I can add 25, 23, and 18. And I think that's 66 centimeters. Would you guys agree there? Big idea. If this point is tangent to those circles, or to that circle, then those are the same. I know it's tangent because it says inscribed.